Alright, in this video, I'll formulate a cool way of getting Euler's constant and also just showcase whiteboard videos. Let me adjust my camera slightly. Alright, because I don't really like doing this on the phone. So let's construct a function e of x such that as it approaches some constant, it equals e, or Euler's constant. That would imply that the limit of x, that the natural logarithm of e to the x equals, as it approaches c, equals 1. Okay, so if we define a function here, right, e to the x as f of x to the power of some 1 over g to the x, then this natural logarithm becomes f of x to the power of 1 over g to the x, right? And following your logarithm rules, we can take this exponential out, f of x, and then we want this to, and it'll just look nicer if we write it as this natural log of x over g to the x, right? So so now we want the following to be true. The limit of the natural logarithm of f of x over g to the x as it approaches c equals 1. We're going to do a weird trick. We want this to be an indeterminate form. So we want, and this is a restriction that our functions g and f have to follow. So the limit as x approaches c, we'll write it as the natural logarithm of f of c over g of c equals 0 over 0. We can simplify this to f of c being equal to 1, so the top part is equal to 0, and g of c equals 0. So if these two are followed, then our form is indeterminate. All right, when we're trying to solve a limit that involves an indeterminate form, we use L'Hopital's rule. So if some limit of f over g of a function f over g is indeterminate, then that is equivalent to the limit of the derivative of f over the derivative of g. I won't get too much into L'Hopital's rule, but that is something important to know. Another important thing to know is that the derivative of the natural log is 1 over x, which, using the chain rule, taking f of x equals f prime of x over f of x, right? So let's use L'Hopital's to say that we have f prime of x over f of x, and then dividing that by f g prime of x. Cleaning this up, get the limit of x going to c of f prime of x over f of x times g prime of x, and then we want this to equal to 1. Okay, so that's our final sort of restriction here. All right, now let's construct a function, or let's construct an f and a g that has the following properties. And we're going to be a little bit more restrictive, but you can form functions that work sort of the same here. Okay, so let me get rid of this part, and we will write it over here. So let c equal 0 to make things simpler, and then that would make f of 0 equal 1 and g of 0 equals 0. All right, and if we make it so that the derivative of x over the derivative of g, again, since we are plugging in 0 and that would equal 1 equals 1, then we have our derivative of f equals the derivative of g, just by multiplying g prime. Okay, if we follow these rules, let's say that g prime, or let's say that g of x equals x. That means that if we plug in 0, then we'll get 0. So this is satisfied. Okay, and if we want the derivative to be the same, it would be, so f of x would have to equal some x plus a constant, because that would disappear. At 0 it equals 1, so our constant here equals 1. All right, so now plugging this into our earlier formula, let me move this over here. We constructed our f of x to be equal to x plus 1, and our g of x to equal to x. You can verify that this gives us an indeterminate form. Exercise for the viewer. All right, so let's take the limit as it approaches 0 of x plus 1 to the 1 over x. Now, and that equals e. We can actually move this to a classical result that was discovered by Bernoulli, the Bernoulli brothers, I believe. This can be converted to the limit as x approaches infinity, and then we can take the reciprocals instead. So we'll do 1 plus 1 over x to the x. That equals e. Let me see if this is viewable. All right, so this is sort of a classical result that they found when they were studying compound interest, that we approached some e, like 2.7 blah blah blah. I forgot exactly. One of the things that you'll see from, I don't know, like MathSlop posts is they come up with some weird approximation, a weird way of writing an approximation of e, and it just amounts to having something like this, and with a really large x. The thing I like about this one is that we can put integers instead. So if you put like the integer 100, I'm getting off track, but if we put integers, then we can just do repeated multiplication, right? And that just sort of makes calculation easier than, if you did some sort of real number. Now, this actually works for any, this can work for an x, for let's say something like an x squared, right here. If we plug in 0, well, for both of these, 2 over x over x, these are their derivatives, that equals 1. So this is satisfied, and these two conditions are satisfied, right? So you can plug that in, and still, if we, again, just say their limit approaches 0, plus 1 over 1 x squared, that would equal e. And you can sort of replace this variable with like, to look like x. But yeah, so let's do a quick recap. All right, so we can construct a function e such that f of x to the power of 1 over g to the x, right? And in order for this to approach the actual uh, e, we must satisfy the following conditions. F of c equals 1, g of c equals 0, and the limit of the derivative of f times f of x times g prime of x equals 1. Now, I'm not sure if you have to put limits in front of here to have like sort of a less restrictive thing, but I think it's fine. All right, and if we follow this, we get our e. So please inform me if I made any mistakes or if this has already been done, and also if this whiteboard format is preferred. Thanks for watching.